So this number e, that actually is on your calculator. Which anytime a number gets specialized on your calculator, it's probably important. You'll see it in a couple spots actually. With the ln button, you'll see it in blue there, e to the x, and then also there's an e there with the division sign. It has two buttons on your calculator. So again, you know that's probably an important button, important thing if it's got two buttons on your calculator. So it turns out E is not just a letter, it actually has a special number. And the technical name for it is called Euler's number. That's the guy's name here, Leonard Euler. Looks kind of like Euler, but it's pronounced Euler. Also could be called Euler's constant or just E. That's pretty much what I call it, just E. So E is this special number, kind of like pi, right? Whenever you see pi, you know that, what do you think? You think 3.14, right? 3.14159, and on it goes, right? This is up there. Same as with E. E actually is a constant as well. It's irrational in the same way that pi goes on forever. It's an irrational number. E is also an irrational number as well. And if you push the E on your calculator, specifically like the blue one on the right, if you do that and then just hit enter, you'll see there, this is the value of E. It's 2.7182818828. And it actually goes on forever too. It kind of looks like there's a pattern there, but it's an irrational number as well. It goes on forever. So these two numbers are pretty important in math, and you could say that E is maybe just as important as pi. I don't know. It's a pretty important number as well. So that's what we're going to talk about today. But the reason we're talking about it is because it's going to be used in our exponential functions. So we're going to be graphing E. And you're probably wondering, well, what is E? How do we come up with it? Because pi, we have a way of coming up with pi. Pi comes from the circumference of a perfect circle is pi times the diameter. And then so pi is the circumference of a circle divided by its diameter. And that's where pi comes from. E is a little bit harder to explain where that comes from, but I'm going to give you just like a little brief sort of glimpse of where it comes from. And you don't need to write this down. Again, it's just going to be a little introduction on what E is, and I don't expect you to fully understand it yet. But one place where it's good to see kind of where it comes from is compound interest. So interest in like a bank, for example, you put money in the bank, you earn interest off of that money, right? If you put $1,000 in the bank and you let it sit there for a year, then the bank is going to give you some interest at the end of the year. It grows interest throughout the year. But typically banks say compound interest monthly. So like every month they would add some interest based on how much money you have in your account. So if you have $1,000, then they'll do like 3% of that. Every month they'll add that interest. So you earn a little bit of money. You might at the end of the year get like 50 cents off of money or something like that. Not a lot of money. Banks don't give you a lot, but you'll get a little bit of money in interest. And this is the formula here, what's called compound interest. And this is how an amount is calculated. This A, you don't have to know this, but you might look at it again another fun time. But this A stands for like the balance at any given time. The P stands for the principal, meaning the amount that you put in. The R stands for the interest rate. The N stands for the number of compounds. So how often this interest is basically added to your account. And then so the same up here, number of compounds. And then the T is the time in years. Okay. So we're going to start with this scenario. Now let's say you put $1 into the bank account. The principal is $1. Right? And your interest rate, you're going to get a really good interest rate. They're going to give you 100% interest. Really good, right? 100% interest, that's unheard of.
Please pardon the interruption. Can the following students please report to room 725 for some information relating to the upcoming State USA Regional?
All right, and then we're going to leave this money in the bank for a year. So we're going to say the time is 1 year. So we're going to put $1 in the bank. They're going to give us 100% interest in 1 year. So if I were to plug this into this formula, my principal, meaning the amount I put in, is $1. I got 1 plus. My rate is 100%. So the rate is always a decimal, but 100% is 1 as decimal. We're going to talk about the number of compounds in just a minute. Then I got n up here, the number of compounds, and the time is 1 year, so that would be 1 as well. Right. So what happens is I'm going to put this function into Desmos real quick. And I'm just going to change the n's for x's. So this function, we'll say 1 times 1 plus. Our rate is 1, so really good. 1 over x to the x power, right? And don't worry about what that function looks like right now. But all right, so here's our formula. So if our interest is compounded yearly, meaning at the end of the year, they're going to look at our balance and then give us some interest. That's called compounded yearly. So one time, it's compounded one time. At the end of this year, we're going to have $2. Okay, so we invest $1, they're going to give us 100% interest, so we get $2 at the end of the year. Now, if instead this interest is compounded what's called semi-annually, anybody ever heard that term, semi-annual? This means twice a year. Okay? So if this interest were compounded twice a year, then I would have $2.25 at the end of the year. So that'd be better. If it was compounded quarterly, that means 4 times a year, then I get $2.44. If it's compounded, let's say monthly, well, that'd be 12 compounds, $2.61. Let's say I want to get this compounded daily. So every day they're going to be adding interest. So that means I would compound it 365 times. All right, and better than that, let's do it hourly. So 24 times every day. So it'd be 24 times 365. That means they're going to compound my interest in a year 8,760 times. And then let's say even better than that, they're going to compound it every minute. So I'm going to take that, and since there's 60 minutes in an hour, I'm going to times that by 60. And then so that means they're going to compound it 525,600 times. And let's do one more. Let's say they're going to compound it every second. So I'm going to multiply that by 60 again. And this is how many seconds are in a year. 3153600. All right. So what do you notice as I compound this more and more? Yeah, it's E. All right. So these numbers are getting closer and closer to E. So what E actually represents is continuously compounding something. So the actual notation, you don't need to worry about this notation, but this is just math lingo, which if you ever took calculus, you would sort of learn this. But what E actually is, the definition of E, we say we want the number of compounds to be an infinite amount of numbers. So we want to compound that continuously. As we said, the limit as n goes to infinity. This is sort of calculus lingo here. 1 plus 1 over n to the n. This is like the math definition of what E is. You don't need to know that. I'm just kind of showing it to you where it comes from. But what this represents is not just money. Let's say like any population, like if you took the mold on the bread from yesterday. The mold on the bread doesn't just decide to grow like once every year, right? It's constantly growing. Or it doesn't say like, oh, the mold is only going to grow once every week, right? It actually is constantly growing. So this represents continuous growth. Same with like the population of the world. It's not just growing, like it's not like babies are born every, once a month babies are born. They're being constantly, born. So this is representing continuous growth, meaning things are constantly sort of being grown. Same with like the fire example. The fire doesn't only expand, every minute. The fire is constantly growing. So this is like a math formula to represent continuous growth here. You don't really have to understand it, but that's where it comes from. And it turns out all that can be represented by e. So when we talk about exponential growth, typically what we do is we use e as our base, and we say e to the x. E to the x represents our exponential growth. So that's a really common base to use. It represents continuous exponential growth. Okay. So Leonard Euler figured this out, and again, the math is a little bit maybe too advanced for this class, but you kind of get the idea here where it comes from. And so we're going to graph it. You don't have to explain all this stuff. You're just going to be graphing it for now. And eventually we'll do some other applications with it. But the good thing about this is it doesn't matter whether you're graphing 2 to the x or e to the x or 10 to the x. The graphs all look pretty much the same. So if we're to graph e, in particular e to the x, so if we said f of x is e to the x, and we're to graph that, it's going to look the same as like 2 to the x. E to the x is going to cross at 1, go up to infinity, and look exactly the same as, like we said, 2 to the x. It would grow just a little bit faster. But whenever you see an e, just remember e is the same thing as 2.718 and a bunch of other numbers. So it's just basically saying 2.7 to the x. When you see that e, it just is the number like 2.7. So that is e, our exponential growth there. And the opposite is true, so this is growth. There, you'll also see e to the negative x. Yes, e to the negative x is actually the same thing as just saying 1 over e, so it's like a fraction. 1 over e to the x. And that represents exponential decay. So it would be the same thing as sort of saying like 1/3 to the x, or 1/2. And so it's the same deal, it just goes, it's just decay. And it has the same asymptote. So everything about graphing it is the same. It's just we have an e there instead of a number. So whenever you see e, just think it's 2.718. All right, and all of this stuff stays the same for both of them as before. So you might not even need to write it out, but the ones you could. All of this is the same as yesterday. The domain is you can plug in any number, negative infinity to positive infinity, or just all reals. The domain. The range is the same as well. It doesn't go below 0. It's 0 to infinity. It never crosses the x-axis, so there's no x-intercept. The y-intercept there is at 1. 1. It does have a horizontal asymptote at y equals 0. And does not have a vertical asymptote. Those are the general properties of E, Euler's number E, or also called Euler's constant. But if you just say E, that's what most people just call it. E, or the exponential function. Okay, so we're going to graph this. Would anybody like some more graph paper? We'll do, one should be sufficient for both the notes and the problems you have to do. All right, so let's graph some. We're just going to do a couple easy ones today, and then I want to give you some time to do them before you leave, so hopefully you don't have homework. so we can enjoy the nice weather on Saturday. Somebody doing anything fun on Saturday? I'm gonna try to hit some baseball. Sonny's gonna play t-ball this year, so yeah, get some baseballs. All right, so we're gonna graph this e to the x minus 2. Nothing changes about how we've graphed this before. Just again, whenever you see e, don't get intimidated by it because it's a letter. It's just like 2.7. So anything greater than 1, we still graph the same way. It goes up to 1, like that. That's our parent function. That gives us going to graph that still. And then we just have that one transformation, which is to go down 2. So we just move our asymptote down 2. Move the point down 2 as well. And we draw it. And theta our domain. Domain is always going to be the same. It's negative infinity, positive infinity, are all real numbers. Our range, which is negative 2 to infinity. And then our horizontal asymptote, which did move, and moved down 2. So now horizontal asymptote is at -2. Whatever the horizontal asymptote is, it will always be in your range, 1, 2 spots. Any questions about that one? Easy. Let's do a couple more. A little bit harder here. Negative e to the x minus 1. All right, we still got it just e here. So when you're looking at e, what you want to look for is to see if the x is negative or not. The x is positive, so it's still just going to be exponential growth here. The next one we'll see, I think, is negative x. It's just exponential growth. E is positive. All right, but then we do have two things happening. We got this negative here, which I'll just reflect. Remember if that's the x and y. Yeah, reflect over the x, which means reflected down. And I'm going to do that first. It's easier to just go do that first. Just take this point and move it down. Reflect it the same distance. Just do this in 2 steps. Anytime we have a reflection, I think it's helpful to just do it in 2 steps. So reflect it, and then we also have to do this. Since in the x move, that means it's going to be left or right. And it's always the opposite, so it's going to be the right one. So then just take your point, move it over 1. We didn't move the asymptote at all, didn't shift it up or down. So let's state our domain in range here. Domain is always going to be the same, all reals or negative infinity, positive infinity. Anybody know the range? Yeah, good, yeah. So the lowest number is negative infinity. It goes all the way down to negative infinity. And you always start with the lowest number, which is negative infinity. And then it goes up to 0, but doesn't touch it, so it's crazy. And then horizontal asymptote, we didn't move, so it's still 0. And again, notice it's in the range. It's the second part of the range this time, but it'll always be in the range. I'm gonna do one more example, and then you guys can hopefully finish the problems before you leave here. Three plus e to the negative x. So the first thing that you want to note is that this is a negative x. So that tells us actually going to be decay. It will go down instead, which is the same thing as just reflecting it over the y. It'll be the same thing. But since we noticed that, we can just go ahead and draw it with that reflection. If you didn't do that, then it's okay, you would still have to reflect it over the y. But we just kind of take care of that step at the beginning because it's a negative x, so we know it's decay. Since we already took care of that, the only thing we have to do is then do this. And just like the warm up, remember this is the same thing as saying like plus 3 over there. So that tells us to go up 3. So we shift everything, shift this one up 3. Shift the acid up 3. I'm going to redraw a function here. What's up? And then I guess we need to do our domain range. Domains all reals every time. Range this time. So range this time. Anybody else? This one together. So 3 to infinity. So the lowest one is 3, all the way up to infinity. Horizontal asymptote then there is y equals 3. Right. Guessing you can handle that? Yeah. Right. So we got 4, 5 graphing ones. Hopefully they're pretty quick.